Okay, today I'm going to talk about convexity. I'm going to talk about the Krein-Milman Theorem, and I'm going to finish off with a cool application, one of the favorite arguments I've seen in a long time. So we'll start in the context of an ambient vector space, V. That's so that I can talk about convex combinations. So a subset D of V is convex if for every pair of elements x, y, and d, and for every real number in the unit interval, so that's t in 0, 1, that should be, those are closed brackets, by the way. We have tx plus 1 minus ty is in D. Okay, so there's a really simple picture to draw here, which is I have some region. Okay, I'm going to claim this is convex. Oh, thank God for the auto corrector. And I have 2 points in here, x and y. And then I draw the line between them. And this is, of course, my ambient space D. I draw the line between them. This stays inside my region. The whole line stays inside the region. So that's a convex body, and that's very straightforward. And I'll draw a few examples of convex bodies. So, triangle, definitely convex, especially if I draw it correctly. Square, convex, we all love that guy. Star, on the other hand, not convex, because if I take these 2 points and I try to draw the line between them, oh, I left the star. It's bad. And you got to imagine I filled in all these shapes, but I trust you to have a good enough imagination to believe I did that. Okay, convexity, very simple, very straightforward. Draw the line, we stay inside. Now, convex bodies have something that we call extreme points. Extreme points are really nice for characterizing these things for reasons we'll obviously talk about later. So let C be convex in V. We say that x in C is an extreme point of C if, and this is a little bit of a weird condition, so take some time to unpack it. Whenever y1 and y2 are in C and t is in 0, 1, and ty1 plus 1 minus ty2 equals x, then actually y1 was the same as y2 was the same as x. Intuitively speaking, an extreme point is a point where it can't be got into as a convex combination of other points unless they were that point itself. So let's look at some more examples of this kind of thing. So if I have a square, look at this beautiful, definitely square looking square. This is probably convex even. If I take, let's mark some interior points in green. If I take this green point right here, I can get to it by drawing the following line between 2 points. I just take this red point and this red point, and I just draw the line between them. Okay, so The red points, on the other hand, actually are extreme points, and this is a little bit of a tricky exercise to do yourself. It's a good first time because you need to kind of figure out the knack for it. But those red points, I'll actually mark them all. Those red points actually are extreme points. If we look at a familiar example, like say an oval, sorry, and again, like we got to pretend this whole thing is filled in just because I'm too lazy to fill it in. If we look at something like an oval, then this whole boundary is our extreme points. It's very hard to get at the boundary because the oval's got some curvature to it. And, that's fun. Okay. Now, for one more example of a convex set without extreme points, let's take the set of x, y in R2 with x squared plus y squared less than 1. So this is the open unit disk. This has no extreme points. This tells us some pathology can occur when our set fails to be closed. This is obviously convex. I'll draw a little picture, a little kind of fake picture, the kind of fake picture I often draw. We've got this open unit disk, and we shade it in. And it's definitely convex, but it doesn't have extreme points. All the extreme points you might expect to have on the boundary, they've just been cut out, and that doesn't change the convexity of the shape at all. But this is enough intuition for us to talk about Krein-Milman, which is the thing I wanted to talk about anyway. So I'm going to put in two pieces of jargon here, technical definitions which I will not explain, and I hope that the listener either knows or is willing to ignore. We need to know what a locally compact topological vector space is. And we need to know what compactness is. And we also need to know closure in the sense of topology. And you should probably be able to follow along without knowing these definitions, but it's a lot better if you do know them. Okay. Here's our big definition. This is the big guy I was hunting down. Sorry, this is not a definition. This is a theorem. Big noob. Theorem. And this is the celebrated Krein-Milman theorem. Let's let X be a locally compact topological vector space, and C subset X compact and convex. Then C is the smallest the smallest closed convex set containing its extreme points. And one way to say this is C is its own, C is the closed convex hull of its extreme points. Well, this is a really cool result. It tells us why the triangle was a good example and the square was a good example, but why the open disk wasn't. The open disk isn't compact, so how could it possibly have this Krein-Milman theorem apply to it? And it tells us that a compact convex set can really be uniquely identified with its set of extreme points, and understanding the extreme points is the same as understanding the whole set, which is really good stuff for us. Now, the people in the audience who have taken a little bit of functional analysis should understand the following issue, which is that a lot of locally compact topological vector spaces have very bad, locally convex. Sorry, this is not supposed to be locally compact. It's supposed to be locally convex. This is actually a really big error, but I can edit it once. So I'm going to cope and not re-record this. Locally convex, that's super important. Locally compact would be totally different. Anyway, locally convex. Most locally convex topological vector spaces don't have that many compacts, and it takes a lot of work to find a topology in which any given set might be compact. But we always have the Monaco-Oglu theorem, which says that every the unit ball of the dual space is compact, and we're going to use that a lot. So I'm going to pose the following question, and we're going to answer it using this theorem in a way I think is really cool. So I'm gonna pose it first using kind of natural language, and second using the language of functional analysis. So say we have an infinite grid in 2 dimensions. 2 is the first kind of interesting example. So the picture you should be thinking about is I'm going to draw the lines here, and I'll use the lines of the one note. Okay. On each vertex of the grid, there's a real number. You can actually do complex here, of magnitude at most 1. And then we're going to have a further condition, which is that each number is the average of its 4 neighbors. Then what kind of patterns can emerge? And spoilers, it turns out all such arrays of numbers are actually constant. So let's do a quick little mini example here. Let's say my number at the center here, let's say I have a 0. And then let's say I have a 1 here, and a 2 here, and a -1 here. Then this has to be a -2. Okay, and I can keep trying to propagate this out. Actually, let's do a 1 and a -1 because it'll make it clearer. So this can be a -1, and this can be a 1. Okay, so you think, well, that's fine. Well, okay, let's say from here, I know the average has to be, there's a 2 coming from here. So maybe if this is a 0, then I know that this is probably like a -1 and a -1, and then maybe that means this thing, if this is 0, this can be a 1 and a -1, something like that. Right, and you can keep trying to toy with this and propagate it around, but you can see that I'm starting to build myself a little bit into a hole here, because if this is a 0, this is 0, this is a 0, and then the average is 1, that means this has to be a 4. So you can see how we can naive approaches here might not work. Okay. So the way to phrase this in the language of functional analysis, which I think is very cool, is we're going to fix our space x to be L infinity on Zn for some, fixed n. And that's the space of bounded functions on Zn with this primum norm. And we're going to let E1 through En denote the standard generators. Of Zn. So these are, 1, 0, 2, 0, 1, 0, and so on. And then there's going to be a translation operator. I'm going to call it the operator R sub EI. Actually, let's just start with an arbitrary group element. We're going to start. Well, you're going to define. So for any group element R in Zn, I'm going to define U sub R from x to x by U sub R of F of an element here, which I'll call, V, is going to equal F of V minus R. So this translates by the input R. And now I'm going to define a kind of averaging operator, T. Whoops. I'm going to define an averaging operator, T. Once I figure out how to not be stupid. From x to x, which is going to do the following. It's going to take an element f, and it's going to send it to the sum from I equals 1 to n. Now I need a 1 over 2n, because I just said it's an averaging operator. And I'm going to apply this to U sub R, F, sorry, not U sub R, U sub EIF plus U sub negative EIF. And if you think about this for a bit, this is going to make sense to you. I add up what's on the left, on the right, on the top, on the bottom, and then so on for each possible cardinal direction in our elements of Zn, and then we'll average them. And then our question is, characterize the kernel of T minus I intersect the unit ball. I want to find the one eigenspace. I want to know which bounded functions are equal to their own averages. And to make our lives easier, I'm going to let C be this set, which is the kernel of T minus I intersect the unit ball. Now, this is pretty obviously a closed set. The unit ball is closed. The kernel of T minus I is closed. And it's pretty obviously convex as well. I've intersected two convex bodies. Now, the problem is C is not compact in the norm compology. C is not... Good God, I'm going to lose it. C is not norm compact, but it is weakly star compact in the topology coming from the pre-dual with L1Z n. Great. So now I have a compact convex set, and I just need to understand its extreme points to understand the whole thing. And this is where, in my opinion, it gets really cool. So let's assume, so now we can apply Krein-Milman. So let's assume G is an extreme point of C. I've assumed it has extreme points. I know it has extreme points because it's got Krein-Milman, and I know if I understand the extreme points, I can understand everything about the set. So I know that G is an extreme point, so G is going to equal TG. So in particular, G is going to equal this big sum, 1 over 2n, sum UEIG plus U negative EIG. What's this? This is actually, and this is the cool part, this is, oops, let's undo that. This is a big convex combination. Our weights T1 through Tn, sorry, T1 through T2n are equal to, actually, are equal to 1 over 2n. And you know our y1 through y2n are equal to UE1g, U negative E1g, and so on. And it's a pretty straightforward exercise. You can check this yourself. A word here meaning I don't want to do it. Each URG is in C as well. Okay, so what I've done is I've said that now we know that G is a convex combination of each UEIG. But as G was assumed to be an extreme point, this means that each UEIG has to be equal to G itself. And that means G is translation invariant. And the other word for translation invariant we can use here is constant. So G is constant. And if every extreme point of C is constant, then all of C consists of constants. Because it's the convex hull of these. And of course I could have done this for any bound. So this tells you the only things equal to their own averages are the constant functions. Which I think is a really cool application of the theorem. So I'm going to do a few small follow-up points here, which I think are just interesting to think about. The first is, for n equals 1, the problem is super easy. And it's so easy it has an elementary solution. And then I want to know, is there an elementary solution for n equals 2 or above? When n equals 1, you're on a strict grid, and basically you can say that any function which is equal to its own average in this sense is it's going to form a line. Can we do that for n equals 2? I had a lot of trouble. I couldn't do it. Second is, we actually really crucially use, this is really interesting, we use that Zn is an abelian group really strongly. And actually, non-amenable groups don't have this property. If you take a non-amenable group and you do this kind of translation setup on it, there are non-constant functions which are equal to their own averages in that sense. And that's really cool. So that shows up in like the Lamplighter group. I never actually constructed an explicit example. It might just be impossible, but it's related to like this non-amenability. Yeah, so I just thought that was interesting. This is not exactly the kind of video I've put out before, but I just think it's cool. So I'm going to put that up there.